Good morning and or good afternoon or good evening, wherever you are. As always, people tend to join a few minutes late, so I'm going to start in just a minute or two. Um, just so you're all aware, this is being recorded, and I am going to go ahead and send the recording link to everybody, even those of you who are participating live. So let's just give it another minute or two, and then I'll jump in and get started. Okay, so I will go ahead and get started. Um, so many of you know me. I'm Rich Kleidman. I'm currently the CMO of AirPhoton. In the past, I've been the CEO. In the past, I've been the COO. But when you're with a small company, you do whatever needs to be done. Um, our company has been making integrating nephelometers since 2012, and I have the privilege to work with some very preeminent scientists, including Dr. Vanderlei Martens, who is our instrument designer and has explained a lot of this to me over the years, including yesterday, where he gave me a lot of additional information that I'm going to share with you. Um, so today's topic is understanding particulate pollution measurements from integrating nephelometers. And here's my outline. It's a long outline, but I don't think it's quite that long a presentation. So just going to go through the basics. So what are we measuring? Talk about the physical structure of the instrument, internally how it works, some theory about aerosol scattering, truncation error, which is very important. Then I'm going to, that's all talking about just basic nephelometers, general nephelometers. And then something we do with some of our instruments is we have the capability to look at different size cuts. And that will also illustrate the point of why backscatter is important. I'll talk about uniformity of the light sources. And then a section, I'll start really talking about the data, how you understand the data and the data units. And then we'll look at some actual data. And we have a recently developed live data dashboard for our instruments. And so hopefully we will be able to do a proper live demonstration. So we're talking about integrating nephelometers today. There's several different kinds. We're talking about integrating. They measure light scattering. So there are some things we can learn from an integrating nephelometer and some we cannot. So mostly we want to relate the scattering to the amount of particles, the properties of the particles, mostly talking about size and refractive index. And then this can be directly related to AOD. I think many of you are familiar with AOD. This is what we call aerosol optical depth. It's unitless measurements that are used by satellites and by ground-based radiometers like Aeronet. And then we can talk about how a little bit how the measurements are affected by particle size and shape. So in general, when you're trying to evaluate capability of and performance of an integrating nephelometer, what you want to look at is the possible angular range of the measurements. Uh, because no instrument can measure the full range of angles, we'll talk about why that is later. There's something called angular truncation error. So that's important, the degree of error and how you account for it. It's important, the uniformity of the light sources you're using internally in your instrument. That will really affect the quality of the measurements. And then in a second, we'll talk about the forward and the back scattering. But again, if you're evaluating the capability of your instrument, you want to look at the sensitivity and the accuracy of both the forward and the back scatter measurements. And of course, you want to take into consideration the number of wavelengths in your instrument. So just physically, what we're looking at, this on the left is a very basic nephelometer. This is again, a very simple inlet. It does no screening for size. This is your measurement chamber. It's hard to tell the size from the picture. It's about 1.5 to 2 feet long. And it holds about 1.5 liters of air at any time. This is the control box. And then on board, almost any nephelometer, all that I know of, will have what's called a clean air reference so that you can, in real time, whenever you would prefer, you can get a zero calibration of your instrument so that you can adjust the data as needed. Cleaner environments would do that less often. Dirty environments, you want to do that very frequently. Now, most often, we're looking here on the right. This is a different model of ours. But again, most nephelometers will be used with a cyclone inlet. That's how you get your preferred size of particles. So most people in the world are interested in PM 2.5 because that's the standard for health. Many are also interested in PM 10. This is a different kind of inlet. This particular inlet, we use pressure taps so that we can measure the pressure drop in the inlet, and then we can accurately control the flow rate. Some instruments will simply use a measurement of the fan speed and relate that to the flow rate. So that's just the physical structure of the instrument. Now, we have to really understand the theory of directional scattering. So if I have a particle here and I have an incident light beam to the particle, so I need to know how that light is going to interact with the particle, and this instrument is sensitive to scattering, not absorption. So if the light beam continues in the same general direction, that's what we call forward scattering. We consider forward scattering to be anything 90 degrees or 0 up to 90 degrees, and then the back scatter is 90 to 180. When we are going to provide the data for an integrating nephelometer, so what that means is we're integrating the forward scatter angles and the backward scattering angles. So, and that will often be reported out as total scatter and back scatter. So internally, this is what an instrument would look like. I'm basing this on the design of the TSI nephelometer, which was kind of the standard for many, many years, although they no longer make these instruments. This is different from our instrument, but this is kind of an industry standard. So what you have is you have your sample inlet, your outlet, you have a light source, you have a detector, and you have a sampling volume, and you have a lot of baffles and light traps to get rid of your stray light. This single light source, or usually it's actually several light sources, it can be a single tunable LED. Most often people are using 3 LEDs, different wavelengths of light. But there are some nephelometers that use only 1 or 2. So if I'm now filling this chamber with particles and I've got my light source on and I'm illuminating the whole chamber, if you follow the beam of the light and how it interacts with the particle and then is intercepted by the detector. So if I'm following this path, so this is a forward scattering path because it is mostly continuing in the same direction. It's a direction of 0 to 90 degrees. If I'm interacting with a particle here, so I'm going to have a backscatter event, and that's what I'm going to measure. Now, the particles will scatter in all directions, but this is the path where it interacts with the detector. Most nephelometers, the TSI design, the Ecotech design, what they use is a shutter, a backscatter shutter. So they have a moving shutter, and they will put this shutter in place, and it will now block all of the light that could result in a forward scattering event. And so now you are just simply measuring backscatter. So what you'll do then is you'll subtract your backscatter from your total scatter if you want to get a forward scatter number, or you simply report total and backscatter. This is not a method that our instruments use. Our instruments don't have any moving parts internally, so we're making a completely separate measurement of forward and back scatter, and then we add the two together to get a total scatter number. So let's go into a little bit of the theory and how this is going to affect what we're able to measure, and how the instrument is effective or not effective, how it operates. So if I have, again, my light source, and I'm interacting with a particle, so these are particles of different sizes, getting to larger and larger sizes each time, and this is just a pictorial representation of the directional scattering. So you can see as I get to larger and larger particles, a much greater fraction of the scattering is in the forward direction. So as I go to larger particles, more forward scattering. Often, this is turned into something called a scattering phase function. Now, you cannot do that with an integrating nephelometer, but again, I'm trying to explain a bit more about the theory. So if I am going to look at the scattering angle and the response, so if I take this point here, which is close to 0, I'm going to have the most response. I can graph that. I'm going to add up my 90 degrees. I can graph that. I'm going to add up my 180 degrees. And if I have the capability to do this over multiple angles, then I can construct what's called a scattering phase function. And you can see here that, especially for a large particle, and I may actually be underrepresenting this here, but most of your signal is going to be in the forward direction, and especially the closer you get to full forward scattering. This is some examples of scattering phase functions from different types of particles, and you can see just what I was talking about. When you get close to 0 degrees, your signal really jumps up. And this is not only dependent on particle shape, it's dependent on particle size. It will depend on the light absorbing properties, which are related to the chemistry. So there's a lot of effects we see that will affect the signal, but we can't necessarily tease out all the parts with a simple integrating nephelometer. Here's another directional representation of aerosol scattering. Again, I have a spherical particle, and what I'm showing here is the blue is a representation of the scattering in 440 nanometers, and the red is representation in 670. So you can see even the wavelength that you're measuring at will affect your directional scattering. Okay, so I mentioned I want to talk about truncation error. So no instrument that I know of can measure complete angular range down to 0 degrees. All nephelometers are going to miss some of the angles, and that starts, depending on your model, around 9 or 10 degrees in the forward scattering direction, and most also miss from 170 to 180. You can see This is going to be more crucial, as I mentioned before, because most of your signal is here. So this area that you don't measure is called the truncation error, sometimes the angular truncation error. Um, and so again, because most of your signal is here, and this is an underrepresentation of the slope, it can make a big difference if you're measuring starting from 9 or 10 degrees versus 7 degrees. So our integrating nephelometers start at 7 degrees. TSI, Ecotech, I believe, start at 9 or 10. So there's a difference in what you're going to miss. And then there are different kinds of nephelometers. I'm not going to talk about those today, but there's something called a polar nephelometer, which is looking at individual angles, and those can typically get down to a lower angular number. So ours gets down to an angle of 5 degrees. Okay. As I mentioned, your scattering phase function is going to be different based on the shape as well. So here we have a representation of spherical particles, plates, grains, and what I'm showing here, this is, again, if you have a truncation error starting at 9 degrees, if you have a truncation error starting at 7 degrees. So you can see, depending on the shape, you might miss a significant portion of the signal based on your truncation error. There are many ways that we take into account truncation error. The most common way to do that is using an angstrom exponent-based correction and applying that to the data on the fly. This has been the standard for many years of how to do it. Our instruments currently also apply this kind of method. This angstrom exponent depends on having multiple wavelengths, so you need to have at least 2 to do this kind of correction. There's also me-based theory correction. What we are implementing now currently, and we'll show you a data dashboard later, is the grasp inversion for our data. Now, I can't really go into grasp today, but grasp is a radiative transfer inversion scheme that was originally developed for AeroNet, has been used in multiple satellites, and now we're applying it to our instruments. The advantage of having a me theory-based correction, or how we do it using grasp, our grasp inversion, is that we can actually fit the data, derive the truncation error correction for the particular instrument and the particular data set. Okay, I've mentioned once or twice just briefly, the number of wavelengths you have can be important because there are single wavelength nephelometers. There are 2 wavelength nephelometers. Most common is 3. That's what ours is. So again, just in the theory, if we're looking at response versus wavelength. So as you go from shorter wavelengths to longer wavelengths, if you're looking at small particles like smoke or pollution, which are very small, the larger wavelengths are less sensitive or insensitive to the small particles. And so you will get this slope. So you can actually use this change in sensitivity to your advantage to learn something about the size of your particles. Are they small? Are they large? In contrast, your dust and sea salt, which are large particles, are mostly insensitive, but in the range we're measuring, again, we have some differences we can take advantage of that in the actually, this should be blue. This is blue, green, red. That you can see that in the blue wavelengths, we don't have quite the sensitivity to scattering as we do in green and red. So these differences help you to understand things about your particle size. Okay, so that's all basic nephelometers. I want to talk a little bit about some advanced capabilities. Um, so one of the things we do is because we're using pressure taps and not just fan speed to measure the flow rate. So we have a very accurate measurement of the flow rate. And because we have the cyclone inlet, we can select the size of particles that we want to look at. These are typically designed for PM 2.5 or PM 10 because that's what people have most interest in looking at. We use one that has the most sensitive size cut at PM 2.5. What we then do is we have the cyclone, we have our accurate flow measurement, we have this fan or blower that we can control very carefully. And so we call it a feedback flow control system. And so we can then use this to select multiple size cuts anywhere from PM1 to PM10. This is something that's programmable, so you can do it on whatever schedule you want to really fully take advantage because in this instrument, the volume is large, about 1.5 liters. It can take up to 10 minutes to get a full and complete exchange of the air from one size cut to another. So this is some data. This is just showing how when our flow rate changes, this is a PM 2.5 flow rate and a PM1 flow rate. So the smaller the particles, the higher the flow rate. And so you can see that we can see a clear distinction here between the PM1 size particles and the PM 2.5. And again, this is just scattering data from one wavelength. Now, well, why is this important that you want the different size cuts? Using the size cuts, you can generate a particle size distribution. And so normally, in most cases, we look at data as fine mode and coarse mode of a bimodal distribution. Each one of these lines is a different set of measurements. But what's nice about this is that if you have a size cut at PM1, that corresponds pretty well to your cutoff for your fine mode aerosol. And then we use the other size cuts to learn more information about coarse mode. Coarse mode can actually be more difficult to characterize because coarse mode might have changes in density, whereas fine mode usually does not. So we're doing an aerodynamic sizing by the size cuts, and then we're doing optical sizing by the measurements using the angular information as well as the wavelength information. Here is some actual data that we took a long time ago at an AGU meeting. And so what I wanted to show you is to start looking at data, and again, why this is significant. So these drops in data, this is, I mentioned the clean air reference. So we were running the clean air reference very frequently. What you will see typically in data is that when you have small particles, you'll see a very, very large difference in your wavelengths. And so that's what's going on here. As this was daytime when there were people in the hall, and this is after people left. And then in the middle of the night, there was this gigantic spike in very, very small particles. We've seen this a couple of times at different venues. And after some investigation and consultation with our friend who's an atmospheric chemist, what she told us is that they're using cleaning solvents either on the carpeting or the floor, and then they're volatilizing. And what you're seeing here is gas to particle conversion. So what this tells us is that nephelometers can be extremely sensitive to small particles if you're seeing the gas to particle conversion, which we were in this case. Okay. Another characteristic that's important for performance is the uniformity of the light source. So in terms of your scattering angle, your intensity of light should really correspond. The theory is that it should correspond to a sine curve. However, if you recall, no nephelometers are going to go all the way to 0 and 180. So this is kind of, in practicality, if it was a perfect sine curve, uh, more of what you would get. Now, what I'm showing here is not just the uniformity of the light source, but also the cutoff and the measurement capability. So again, it's important to get a total scatter and a backscatter, and I'll show you why in a minute, or a forward scatter and a backscatter. So this, when you're using the shutter, and this is from published data. This is not something that we created. So an aurora nephelometer, which uses the shutter, and I assume a TSI would be the same. So this is actually your backscatter fraction. So, in theory, you really want a straight line right at 90 degrees. So the shutter has some inaccuracies. Our method has some inaccuracies as well, but for the most part, we're pretty close to that 90. And then we make these corrections in our data handling so that we do wind up actually with a very nice distinction between forward and back scatter. And here's one of the reasons why that can be important. So again, these are some measurements that we made, and now we're varying the flow rate to go from PM10 to PM2.5. So when we're looking here at the total scatter, you can see these jumps would correspond to when we're going at the slower flow rate. So we would pull in all the particles, including up to PM10. And you can kind of see a distinction, but it's a little bit muddy. It's not so clear. When we look in the backscattering, and again, this is just one wavelength, this is green. And again, changing the flow rate between a PM10 slow flow rate and a PM2.5, we get a much clearer distinction between these two size cuts. And so this is often what you're able to see using backscatter versus total scatter. Often the total scatter gives you an advantage, but there's times where you can get more information from the backscatter. Okay, so let's talk a little bit now, understanding the units of measurement for nephelometers. So this is all based on the Beer-Lambert law, and we're describing how the light intensity is going to be decreasing exponentially with distance as it comes through our sample volume and interacts with the light. So here what we want to know is the attenuation. What's the transmitted light intensity? That's based on your initial incoming light intensity, your scattering coefficient, and the length of the path, right? The longer the path, the more particles you have. So the standard unit of measurement is we use something called inverse megameters. It's odd, it's not intuitive, but basically the reason we're using inverse megameters is because in this equation we have a distance factor. That distance is kilometers, or megameters, if you will. And so therefore, the scattering coefficient has to be in inverse kilometers or inverse megameters. Okay, so that's the best I can do for explaining kind of in an intuitive way why we look at and why we report out in inverse megameters, because we rearrange the equation to report out the scattering. One of the nice things about this is that it gives you an easy way to compare with AOD, and it's also useful for radiative transfer models. So if we're looking again at what's happening inside, so here's again a theoretical drawing of what it might look like um, in our nephelometer. If it's completely clean, there's no change between the initial intensity of light and the light after extinction because there's no extinction or scattering events. Um, Now, if we come down here and now we add a lot of potential scattering extinction events. So now we're going to get a signal, which is going to be dependent on the number of particles and the length of our path. But I also wanted to take a second here to explain why you can't get a measurement that goes down to zero. Um, the only way to get zero scattering with no change in direction, right? Your incoming light source would, say, interact with a particle right here and continue on to the detector. If you do that, you're going to blind your detector. So you have to have some offset and some way of accounting for stray light so that you're not blinding your detector. So there are many ways to do that. The closer you want to get to a zero angle, the harder it is to take into account the stray light and to make sure you don't blind your detector. Okay, so what are some of the factors that are going to affect our numbers, our measurement, what we're seeing? Well, particles are not all uniform. I mentioned before you have different sizes, but you have different shapes. You have, of course, your concentration, so your distance, your path is going to be important. The cross-sectional area of the particles is going to be important, and the light absorbing properties of the particles is going to be important. So that's all going to affect your signal, but not all of these things, you're not able to tease out all of these individual elements uh, accurately. Some you can, some you can't. Some it helps to have the multiple size cuts. It helps to have a grasp inversion. So we can say something about particle typing. So when we're talking about particle typing, we generally mean, is it sea salt? Is it dust? Is it biomass burning? Is it smoke? So we can generally say something about particle typing using all of this information. Um, just I wanted to mention here that I have said a couple of times that you can relate your scattering coefficient to an AOD. So um, if we're looking at AOD, which I'm used to from years of being an aerosol scientist looking at satellites, I know that these numbers, even up through 0.1, is pretty clean. In more polluted parts of the world, you're going to you're going to get up to these numbers, which we don't often see in Europe or the United States. So this is just for reference and interest. One more thing that I only learned very recently. One of the reasons that this whole development or division into forward and back scatter had to do with climate. So if you've got your downwelling radiation and you've got your particle here, you want to know how much of your downwelling radiation is going to transmit through the atmosphere and get to the surface. Well, and you want to know how much is going to reflect back out into space or back out into the upper atmosphere. So when you're integrating your signal, really what you want to know is the up scatter versus the down scatter, the up scatter fraction. This is important for climate and radiation. So I just thought this was interesting. We don't generally take advantage of the climate implications when we're measuring from an integrating nephelometer, but that information content is there, and you can link what you're measuring in an integrating nephelometer or a polar nephelometer to your satellite measurements, and this is something that many people have been doing or attempting to do for many years, and it's something we have several pieces in place at GRASP uh, to link those satellite measurements to column measurements to ground measurements. Okay, so I wanted to take a minute now and look at some actual data. Um, so let me pull over this. Okay, so this is some actual data. I hope you can see this well enough. This is from an instrument uh, operated by a research institute in Ahmedabad in India. And so this is one of the instruments that measures at multiple size cuts. Okay, so this, what you're seeing here, this is all of the data, and you can see as it changes flow rate, this is PM10 and everything smaller. So when I say a size cut, it's not a size bin, it's a size cut. It's 10 and everything smaller. Here it's PM5, PM4, sorry, and everything smaller. Here we've got PM2.5 and everything smaller. And here we've got PM1 and everything smaller. One of the things you can see is as you go to the smaller and smaller particles, you get a larger separation between your wavelengths. And down here, I have the backscatter information. Now, at this scale, it's really hard to see differences, but most of the information content for this particular day, for this particular set of information, came from the forward scatter. Sorry, from the total scatter. And even if we're doing a size cut from PM10 and everything smaller, these particles are dominated by small particles just based on looking at the difference in the spectral response from blue to green to red. If I go here, and now I'm just taking the data from the 5 liter per minute, which corresponds to PM 2.5. And this is a little bit busy because I included total and backscatters. So maybe not the best one to look at, but we'll look at some others too. And then this is just looking at the PM10 size cuts only. So this is basically total scatter, right? This is PM10 and everything smaller. And again, you can see differences, change in concentration. This is our backscatter number, backscattering coefficient in inverse megameters. Again, mostly dominated by small particles. Now, to be honest, really there should be more separation between the green and the red. And that may have to do with this instrument, which we are not operating, needing to have a better in-field calibration, or to have the calibration coefficients reapplied to the data. So that's something that's frequently done. Okay, let me show another one. Okay, and then again, this is our 5 liter per minute, RPM 2.5, and you can see there's a cleaner and larger separation between our spectral response. So again, this is what I would expect at PM 2.5, right? That this is going to be a cleaner separation in the spectral response because these particles are smaller. And I wanted to show one last one. This is a very busy slide, so give me a minute. So the SPARTAN network operates approximately 30 instruments around the globe, including one of the people who is joining us. He operates one in Israel. So hi, Ellie. So what I'm showing here from a Spartan instrument in Beijing is these lines here, the solid and the dashed lines. So this is their PM10 and their PM 2.5. Again, large separation. So you are seeing something that is mostly dominated by fine mode. And this was very interesting, and I didn't have time to show it here, but I compared it with AeroNet data, and you see the exact same very sudden drop off in the particles. So it's very interesting. It would make an interesting case study. Anyway, here I'm looking at the ratio of these are ratios of the total scatter to the backscatter. So that should tell me something about am I dominated by large particles or small particles? If I'm dominated by small particles, then my ratios should be higher than if I'm dominated by large particles, where most of my scattering is in the forward direction. Uh, this was a very interesting case. We're still puzzling this one out. I'm not sure why we're not sure why these differences, expected differences in ratio kind of disappeared here, but be that as it may. So this is just some examples of what the actual data will look like in terms of just your raw scattering numbers and scattering coefficients, which are corrected for truncation error, for zero calibrations, for span calibrations. Okay, so let's go back here. Okay, so I think what we're supposed to have next, if they're on, is Juan Carlos, who works at Grasp Earth he's in Spain actually, and they have created a real-time data dashboard. This is new. This is very interesting. So if you have one of our nephelometers, please
Yes.
follow up and make sure you get the data dashboard. So I've stopped sharing, and I'm going to let Juan Carlos take over here for a little while.
Okay. Hello to everyone. I am sharing the screen now. This is our new version of the Nephelometer desktop application. Is the idea behind this software is that is multi-platform for any operating system, and with Grasp integrate for process the nephelometer data. This is right now in real time one nephelometer that we have here in the office in Spain. We have included in the real-time dashboard at the beginning the temperature, humidity, flow, and pressure. We can see here the time series, how is the flow rate and the target flow. We include the total scattering and back scattering. All this application is under development right now. This part will be generic, and the user can select what the type of plot that he can show in the dashboard in close in real time. And in these two plots, we have the radius of in the two mode, and the volumetric concentration. All these results are with grasp, is close to real time, it's 1 minute delay. We can process historical data too with in the application. You can select any data that you have from the instrument on the past and process with grasp and obtain the results. For example, this is another day. This is April 24, and this is the result of the processing. The idea is that behind this is the AirPhoton instrument suite for include every AirPhoton instrument and have the processing with grasp. This is related with the software that is under development, but we are working to have a first version stable for release very soon. And related with the science behind the processing with grasp and obtain this product, I think the better person to talk about this is the Fernando Rejano, is part of GRAS Spain, and he's working with the science behind the nephelometer. Fernando, are you connected?
Yes, hi, Juan Carlos and everyone. So just to give some details about this aerosol retrieval that we are retrieving using GRAS, in this new application that Juan Carlos is explaining. Now we introduce GRAS in this application, so we are able to retrieve GRAS products in near real time. But we have to mention that these two main aerosol products that we want to retrieve, which is the median radius of the log normal distribution that we are assuming for the aerosol, and the aerosol volume concentration. These are two products that is still under development using GRAS, because there are some thing that we have to optimize in GRAS. But just to give some detail about how we are retrieving these parameters, like we are giving some, for example, when we are measuring with the nephelometer using only one cutoff, so we don't have too much sensitivity to retrieve too much information of the aerosol side distribution. But using some a priori information of the aerosol volume side distribution, we give this a priori knowledge to the inversion, and then we can adapt the fine mole log normal distribution and the coarse mole log normal distribution. And that is what we can see in this plot that Juan Carlos is showing. And also we have the aerosol volume concentration, because using GRASP we can retrieve this parameter. We have the total aerosol concentration, and at the same time we can split the contribution of the fine mode and the coarse mode. Obviously, this is an integrated nephelometer in AirPhoton, and using a GRASP algorithm we can retrieve more parameter, more sophisticated and accurate parameter. But using this integrated nephelometer like an operational product, we are working these two main products. Okay. Anyway, if we plan to measure with the nephelometer using a flow rate scanning, so if we have several cutoff measurements, so we can introduce all this information, give to the GRAS, and then with different cutoff, we will be able to retrieve a more accurate side distribution parameter. But just to mention a bit this.
Thanks. Thank you both, Fernando, Juan Carlos. Fernando, could you just take a second and just mouse over this size distribution and just leave it a second or two so people can see what that data is? Yeah.
Sorry.
Yeah, just leave your mouse there so that people can see the numbers.
Okay, is yeah, yeah. So Juan Carlos, you can okay. Yes, is but anyway, this the thing that we want to show is like we have the measurements display here in the two first panel and the bottom panels. This is the grass retrieval. Okay, so it seems like all of this is the measurement of the nephelometer, but not. We have the optical properties and then we have the retrieval. Okay, so and you can see that, for example, we are assuming a bimodal size distribution for the aerosol. For example, in the radius, we are showing them when we say mode 1 and mode 2 are associated to the fine mode of the aerosol and the coarse mode, and also we want to display this standard deviation, this shaded area, and this will represent the standard deviation of the log normal distribution. So right now it's like a fixed data. You are the thing that is screening the in the plot, but we hope that when we take the nephelometer deploy in a specific site, we will be able to see how the median radius of the fine and coarse mode respectively are changing along the time, and also this shaded area will represent the standard deviation. So sometimes you will have a more wide distribution, sometimes it's more defined. Okay, so but and the same for the aerosol volume concentration. We have just the value of when we integrate all the volume concentration in this fine mode and coarse mode concentration. But I want to remark that we are working on that, and we need more validation about how grass can retrieve this product using one cutoff, several cutoff, using other approaches like neural network. So this is something that is still under development, but in the future will be available for everyone to have this basic aerosol product in near real time. It's a valuable, this added value for our nephelometer and all the processing using GRASP.
Yeah. Thank you, Fernando. Just to be a little more clear, one of the things we developed using graph inversion with machine learning is capability to take the raw data from the nephelometer and to turn that into a dry mass calculation. So I mentioned the SPARTAN network. There are approximately 30 sites out there. I think Dr. Chong Lee took data from 18 of those sites and worked out a grasp inversion with machine learning that we can now turn that information into PM 2.5 dry mass. And so one of the things that Chong has done, she did a correlation for all of the sites. It's about 0.85, so the results are quite good, but we're still working to improve it, as Fernando said. And also, not all of the nephelometers are able to do multiple sizes, but we're working on a capability to retrieve the size distribution or a calculation of size distribution, even just from a single flow rate where we're only measuring, say, something like PM 2.5. So that's some of the things that Fernando was referring to. I want to show one quick demonstration and then we'll go to questions. Fernando and Juan Carlos, if you have a minute or two to stay to help me with questions, that would be useful. So let me just share something. Okay, so I hope you folks can see this. So this is what we can do with the size cuts. And this is an older inversion, even before we began to apply the grasp inversion. So this is what you were seeing with those in the software at the bottom of the screen. But here is some real data that we collected. And so what you're seeing is the scattering from each of these size cuts. And here you're seeing how this has been processed to provide a full size distribution. So this is the capability you have, but only when you there's an instrument we have which does PM 2.5 to PM 10, but unless you go down to PM 1, as I showed before, you're really not going to have an accurate information about the fine mode aerosols. So let me stop sharing this. I see that there are a couple of questions in the chat. So let's see, and then we'd be happy to take any other questions. So first question, is it possible to install these instruments at the street level at human height, or is nephelometer mainly meant for rooftop use for background measurements? No, we actually, you can deploy it anywhere. And it is actually meant to be deployed at street level. This is what I mean, there are research purposes and reasons to protect your instrument where sometimes you want it on a rooftop, but the intention is, and the design is, so we very much want to be able to understand these measurements at nose level and then later relate it to the full column measurement and the satellite measurements as well. What advantages does such an instrument have compared to a street level TPM and a clarity node? So I'm not really familiar with the TPM. I am familiar with clarity. It's a matter of, I believe, accuracy and capabilities and angular information, as I was mentioning. The clarity node and many of the other inexpensive instruments that are out there are basically particle counters. And every instrument has assumptions. I showed you our assumptions in terms of truncation, but particle counters are subject to many assumptions. They're subject to drift over time. There's certain kinds of particles that they have more difficulty measuring. I can't really go into all the details, but if you would like to send me an email, I would be happy to discuss that further. So let's
And
open it up for
Rich,
questions.
just to add
Yeah,
some information is
please.
important because for our instrument is like a very versatile instrument. For example, now we are focusing in one topic, which is air quality, but anyway, the nephelometer can support more scientific lines. So this is like a very versatile instrument that I want to remark that there are a lot of field of related to atmospheric science that we can support information. And also there is an important thing that using the nephelometer, we are working also in retrieving aerosol product in a synergetic way using the absorption measurement and scattering measurement using GRASS that will provide more accurate and complex aerosol products. So anyway, every I don't know exactly these two instruments, but I hope maybe that are a gravimetric instrument based. So this
Yeah.
is at
Thank you
the
for
end,
that.
we have to validate all our PM retrievals with gravimetric instrument. But
And that's what we did. That's what we did when Chong developed our methodology for deriving PM 2.5. And when I mentioned this correlation of 8.84, I was not clear or specific. That's the correlation of our real-time PM 2.5 retrieval compared to the gravimetric measurements from the SPARTAN network. And the gravimetric measurements, where you're actually weighing the mass, that is really the gold standard for looking at PM concentrations. And the PM 2.5 calculation that we make is a dry PM 2.5 mass, which is what is often preferred by the health community, but we actually can provide both wet and dry PM 2.5 mass. So I think that's all I wanted to cover today. What I did not have time to talk about, which Fernando mentioned, is we've done 2 additional things with our nephelometer in addition to the development of the particulate mass, the PM 2.5 mass calculation. We also have developed a joint aethelometer nephelometer inversion. We are hoping to collaborate with McGee Scientific, who are one of the manufacturers of aethelometers. I didn't have time to go into that today. I didn't have time to go into our work on dry mass. We have those presentations. If you go to our website, graspearth.com, there's a webinar page which includes past webinar links. And so you can go and find more information. Let's see. We have another question. For Neph size distribution retrievals, are there any ongoing validation using measurements such as SNPS, APS, or any others? Fernando, do you have any information on that?
I have reply, by the way, in the chat that this
okay.
is the thing that this is our main goal. This validation using this SNPS and APS. So I remarked that all these air quality products related to PM or site distribution retrieve by GRAS is something that we are preparing. We are optimizing GRAB. We are close to finish, and then start the validation phase that is not done yet.
Yeah, there's a lot of work in progress, a lot of pieces to upgrade, advance, validate what we can do with these instruments, but also making that connection between the satellite, the column, and the ground measurements. So we have many pieces in place, and we're working on connecting all of those. Any additional questions? Okay, well, you can find our website. You have my email because I emailed all of you. So if you have any additional questions, please feel free to reach out and contact me. And if I don't know the answer, I will forward it to those who do know the answers. Thank you for your time today. And I hope this was a useful presentation. I would appreciate some feedback if there are topics I did not cover or should have covered in more depth. Please let me know. There'll be another session in several hours, and hopefully if there was any real lacking in my presentation, I can go ahead and correct that or add those pieces for the next one. Thank you again for joining us today.
Thank you.